Hi everyone, welcome to the Earth Science Regents Review podcast series created by Hammock's Middle School Earth Science Department. Today we're going to be talking about a phenomenon called specific heat. Now the true definition of specific heat is basically how much heat energy is needed to raise 1 gram of a substance 1 degree Celsius. Now an easier way to remember that is basically how quickly or how slowly something's going to heat up or cool off. Now when dealing with specific heats, every single substance on the planet has its own specific heat. Every substance on the planet heats and cools at its own rate. Something that has a very high specific heat is an example of water. Something that has a very low specific heat, a good example of that is going to be lead. Now the reason why we gave you those two substances, because they're going to be the two extremes on your reference table, page 1, specific heat of common materials. So make sure you check out my podcast on that page as well. So let's see what high specific heat means. It's all about how quickly or how slowly something's going to heat up. Something with a high specific heat heats and cools extremely slowly, needs a tremendous amount of heat energy to heat and cool off. Well, we gave you the example of water, and the reason why water has the highest specific heat of any substance on the planet is, first off, it's highly reflective. So it takes a long time for that energy to be absorbed, especially when water is going to be reflecting sun's energy off its shiny surface. And B, it's transparent. Not only does the surface of the water get heated, the middle of the water gets heated, and even the bottom of the water column might get heated as well. So there's a tremendous amount of volume that needs to get heated up. That's why water has such a high specific heat. Heats and cools very slowly. And you can see here that 4.18 joules per gram is going to be the unit here. So when you're dealing with specific heat, basically how that's going to be interpreted is water needs 4.18 units of heat energy, or joules, to raise 1 gram of water 1 degree Celsius. Now we compare that with a substance with a very low specific heat, means it's going to heat and cool extremely quickly. An example we gave you there was going to be lead. We know lead is a metal. Metals tend to be extremely good conductors of energy. So lead, and really a lot of your metals, are going to heat and cool extremely quickly. That's why your frying pans, for instance, are going to have plastic handles or rubber handles. You don't want a metal handle, very simply because the pan is going to heat up very, very quickly. So when we talk about low specific heat, take a look at the heat energy here, 0.13 joules of heat energy to raise 1 gram of lead 1 degree Celsius. So significantly lower than water. So keep going with the water aspect here in terms of its high specific heat. The thing is with water is that your oceans, which are a major, major volume of water, take all summer long to heat up, and they take all winter long to cool off. Because water has such a high specific heat, oceans really tend to heat up from February all the way to about August. It really takes a significant amount of time for our oceans to heat up. So your summertime temperatures tend to be a little bit cooler in the water, which means that the air above it tends to be a little bit cooler. Well, it takes all winter long to cool off, basically from August to about February. So when you're dealing with a significant amount of heat energy that's being retained throughout the winter, those oceans tend to be a little bit warmer, meaning that the air tends to be a little bit warmer. What's important about that, that's going to have some major climatic issues regarding our coastal regions. We compare that with land. Land, which is extremely dark in color, is going to heat very quickly in the summer and get very hot. It's going to cool off very quickly in the winter and is going to be quite cold. So very simply because dark colors tend to not only be good absorbers, but they're also good radiators of energy as well. So very, very different specific heats between ocean and land. And the big thing here is that the specific heat of oceans and the specific heat of land are going to have major climatic issues regarding cities that are located in those regions. So what will happen here is that you can compare coastal temperatures versus inland or continental temperatures, and you'll see a stark difference between them. This is very simply because water is going to moderate the temperature. Because water takes all summer to heat up and all winter to cool off, your water tends to moderate coastal region temperatures. So these cities along the coastal regions tend to have quite different temperatures than areas that are much more inland, far away from large bodies of water. So let's take a look. Your coastal regions tend to have very cool summers, very simply because the oceans are quite cool, the air above the oceans tend to be quite cool, which are going to cool off the cities that are somewhat coastal. If you've ever been to the beach during the daytime, you'll get a nice breeze off the ocean. That's very simply because the ocean water tends to be a little bit cool. Well, coastal regions tend to have a little bit warmer winters because the high specific heat of water retains the heat energy from the summertime doesn't want to give it up. So if the oceans are a little bit warmer, the air's a little bit warmer. So what will happen here is you do not get a huge difference in temperature between winter and summer. They tend to be a little bit more moderated because the water moderates the coastal regions. You compare that with your continental or more inland regions. Because land heats up so quickly, you're going to have really hot summers. Because land cools off very quickly, you're going to have very cold winters. So you will have a very big difference between your summertime temperatures and your wintertime temperatures. So when you look at a graph like this, you're comparing two cities. City A is going to be the solid line, and City B is going to be the dotted line. You notice that City A has a huge difference between your average temperature from winter to summer compared to your City B's temperatures from winter to summer. City B is much more moderated. That must be closer to the water. City A has a huge difference in winter to summertime temperature, means it must be a little bit more inland. And again, you just take a look at some current values here. We're going to kind of focus on some wintertime temperatures. If you notice in the northeast part of the country here that I've just circled, you notice that some of your temperatures, notice that you have a 56 compared to a 48, so your 56 is a little bit warmer, your 48 is a little bit cooler, a little bit more inland, tends to be a little bit cooler. Well, you compare that with some summertime temperatures in that same region. Notice now along the coastline is about 62, a little bit more inland is about 73. It's exactly flip-flopped in terms of your temperatures. Coastal regions tend to have cooler summers. Coastal regions tend to have a little bit warmer winters. Your inland regions tend to have a little bit of a warmer summer, and your inland regions tend to have a little bit colder winters. So your coastal versus continental temperatures tend to be a little bit opposite. So that's about it for now. Hopefully we cleared up some concepts here with specific heat, and we'll talk to you soon. Bye-bye.